Okay, so this just a short introduction, ergodic theory of numbers. So the idea is I will start with a little bit with some examples, show you some common denominator between them, that they all are generated by iterating some map. And then I will talk a little bit about ergodic theory. And then we'll go back to the examples, show that all of them are ergodic, and try to deduce some properties from that. And then I will talk a little bit about the notion of natural extensions. And if I have time, I will talk more about beta expansions. Now, I did prepare some lecture notes. They are already on the website. Yeah, and okay, so as I said, the idea is just to show how simple ideas in ergodic theory, actually just basic concepts, can be used to understand a lot about number theory, number theoretical expansion. So let me just start with some like sampler of examples, and then I will elaborate more on them. So let's keep in mind some examples which probably most of you that are familiar with. The first one, let's just look at what we call m-adic expansions, or expansions in integer base. Which means here I'm looking at points x that can be written as a sum of bi over m to the I from 1 to infinity. And here m is an integer, greater or equal to 2, integer. And bi, although you can be very general with these, but I'll stay simple now, are just 0, 1 up to m minus 1. Another example that will come into play is the same idea, but now we don't expand with integer base, but with non-integer base. So these, what are known as beta expansions. So here x is the same form, except the m is changed to beta. And here beta is greater than 1. And I want to take it real because the integer case is included here. So non-integer. And BIs, again, you can be very general with these, and then more questions will come in, how big is the set. But now I will concentrate on also the classical case where the BI is between 0 and entier beta. So the greatest integer less than or equal to beta. Another series expansion is what we call the Luroth series. This might not be that well known. These were introduced actually in, I have them in my 1888. Let me see the time. To scan a little bit more. I think very, very old. Oh yeah, here you go, 1883. By Luroth. And here the idea is that you can write x as a reciprocal of integers. So it looks like 1 over a1, and then this is the only one which doesn't have a uniform form, and then here n is 2 to infinity, and this looks like 1 over a1, and then a1 minus 1, and then a2 minus 1, etc. until okay, so let me just write it, an minus 1 minus 1, an minus 1, and then an, like this. And all the a's are integers and greater or equal to 2. And you can look actually at a more general form, what we call generalized Luroth series. Generalized Luroth series. And these are where you can write them as something like hi over s1 up to si, I from 1 to infinity. And here the hi's and the si's are positive reals. And another famous example, which is familiar to most of you, is the continued fraction map, or any other family. There are lots of continued fraction maps. But let me just stick to the classical one, where, of course, you can write x as 1 over a1 plus 1 over A2, etc. And here the AIs are integers greater or equal to 1. So these are like just examples to keep in mind. And there's a common denominator between them. Namely, everything can be generated by a map. So let's start with the first one. So how do we generate this? So basically, for the first example, so for example 1, you look at the map T defined on the unit interval. Just given by mx modulo 1. And basically what you do, let's keep in mind, let's say m is 2, just for simplicity. So you get what you call the binary expansions. And the map is just, in this case, we have two maps, or two branches. One is 2x, and the other 2x minus 1. And in general, you will have mx minus 1, mx minus 2, up to mx minus m minus 1. So this is for the binaries. This is the map that generates them. And how do you generate? You just first find out where your x is. Are there colored chalks? Okay, you find where x is, and then if it so this you think about it as the 0 region, and this is the 1 region. And if you are here, then your first digit b1 would be 0. If you're here, b1 would be 1. And then to find out the next digit, you look at its image. So if it's on the left part, you go here, and then you look where it is the next time. So in this case, it happens to be here. Then the next time is also 0. That's b2. And then you look at the image of tx, and you look where it lies. In this case, it looks like it is in the 1 region. So then b3 is 1, etc. So by iterating this map, or by following the orbit, if you like, of a point, you can find out the whole expansion. And actually, just want to do it because all of them have the same idea. What the idea is, you define your digits as a map that depends on x. So if x is fixed, I drop the argument. And I just say, I define the first digit. I just say this is 0 if x is in the left part, and 1 if you are in the right part. And if you do that, then you can actually rewrite your map in one form, that this is tx, let's just take m is 2 now, 2x minus b1, which depends on x, of course. And the idea is to get the expansions. First, you solve for x. So you bring the b to the left and divide by 2, and you end up with x equals b1 over 2 plus tx over 2. And you can see this is the first digit, and this is the error. And then to go on, you think of this as a new point. And you, maybe I should do it. So you can, before I go on, let me define further digits, bn, which of course depends on x, by saying this is just b1 of the nth minus 1 iterate of x. These are, of course, not powers, but iterations. And then you apply the same idea here. So let me take the half out. And then tx, I imitate what I got for x. So this is equal to its first digit over 2 plus t of it over 2. And its digit is what we call b2. And then, if you simplify, you can see that you're getting the expansion bit by bit. And you go on. So if you keep doing this, after n times, let me just do here. So after n times, you get the nth digit, and then the error. And these all lie in the unit interval. So this goes to 0. And as you can see, you get the infinite expansion. And this is the whole idea of all of these. So the whole point is to find a map and to try to write it in this way. And then by iterating, you get the expansion. So for example, for the beta expansion, so for example 2, the map is, OK, I want to, classically, you do it on 0, 1, but I want to expand my interval. Because if you think about it, here's my digits. So in essence, I can expand points in an interval, the following interval. The smallest you can get is if you put 0, 0, 0, 0, and then you end up with the point 0. And the largest point you can get if all the digits are entier beta, and then you end up with the point greatest integer beta over beta minus 1. So I want to expand my horizon a little bit because as a preparation for later. So now my map is actually defined on a bigger interval to itself. And the map is simply Tx, if I want to write it rigorously, is actually beta x modulo 1 if you are in the unit interval. And it's beta x minus entier beta if you are in the leftover part, like this. And the map, if I make a figure, let me just take that entier beta is 2, just for simplicity. And the way you do it really is starting from 0, you take intervals of length 1 over beta. If I wanted to, OK, 1 over beta. And you keep doing it until entier beta over beta. And the last interval usually is longer, the last one here. And then here you have beta x. And this is beta x minus 1. And you keep doing it. And then the last interval is usually the largest. So in this case, my entier is 2. So I end up like that. And this point here is 1. Dynamically, actually adding this is a bit redundant, because if you look carefully, then you will see, maybe I should do a diagonal. 1 lies somewhere here. And if you are this block here, or the interval 0, 1 is what we call as an attractor. Once, if you are in interval 0, 1, you will never leave it anymore, because if you're here, the highest you can get is 1, and here also, and here you're under 1. So if you're here, you'll always stay in 0, 1, and that's what classically was studied, really. And if you are in this big interval, because you lie under the diagonal, every time you apply the map, you go to the left. So eventually, you will enter 0, 1, and you will stay there. So dynamically, really, 0, 1 is what's interesting. But the point is, maybe I didn't mention it before, these expansions with integer base are basically unique. There's only one expansion, except for points, for example, in here, except for dyadic rationals. For example, if you go back to the first example, half, I have a choice with half. I can either put it in the 0 region or with the 1 region. And points of the form k over 2 to the m, if you start applying 2x modulo 1, in this case then eventually these will get mapped to half. So what I'm trying to say is that these points have 2 expansions, one ending with 0 and the other one ending with 1. And these are the only one with 2 expansions. Everything is unique. On the other hand, here, although is not very clear from this picture, but there are uncountably many representations of this form. You can, typically, for almost every point that is on a set of measure 1, almost every point has uncountably many representations of this form. Actually, this is a result by Sidorov, who gave later with a student of mine another proof. And this is one possibility of expanding in base beta, is to use this map here. But in essence, what I'm trying to say is that if you are in here, you will start first with digit, in this case, 2, 2, 2, 2, and eventually you will enter 0, 1, and then you will only be working in here. Let me just elaborate a little bit on expansions that you have more than one algorithm. This is what people call greedy expansion. And in fact, it was studied It was first introduced by Régnier. He wanted to give examples of expansions where the digits are not independent. And then Perry studied it really extensively, and he found the invariant measure, but that I will come to it later. Let me show another algorithm that generates expansions also of this form. Which we call lazy. Oh, I didn't give you the expansion. Wait, I want to elaborate on it. So you can do the same thing. You can, in this picture, for example, this is the 0 region, this is the 1 region, and this is the 2 region, if entier is 2. And you can do the same thing. If you look at this map carefully, you can actually also rewrite it in the form beta x, tx is beta x minus the digit, which depends on x, and the digit b1. In this case, it will be a 0 if you are between, let me just take beta, the example. And it will be 1 if you are here. And it will be 2 if you are from 2 over beta to the end. So the end will be this in this case. And if you do this, then you can sort of write the map in one way. And you can see I have the same procedure exactly. I first solve for x, and I get the first the first digit. And then I apply the same procedure to tx, etc. So after n times, you get the first n digits. Where again, the bi's are defined as the b1, let me write here x, the b1, bi of x is b1 of ti minus 1x. And because everything lies in a compact interval, these go to 0, and that's how you get the infinite series. OK, another way, for example, to get the beta expansions is to be lazy. This is greedy. Like at every step, you are sort of taking the largest possible digit. But you can do it in a slower way. I'll keep this here. You can do it in a slower way by doing this. Let me just do the map, the figure. So this is the greedy. And you can do in a lazy way. The maps will all be beta x minus a digit minus an integer. But this time, instead, here I started with 0, and I started taking intervals of length 1 over beta, at each step. And actually, I take as many of them as entier beta. But I can do the other way around. I can start with the right endpoint and start taking intervals of length 1 over beta. And I do it entier times, entier beta times. And then I end up with this map. Like this. So this is still beta x, and this is still beta x minus 1, and this is still beta x minus 2, the same thing. But I'm taking parts of the lines. Yeah, different, that is, I'm taking different partition of my interval. This also generates expansion in the same way. You can do exactly the same idea with the b1s now, also 0, 1, and 2, but defined on different intervals. And you can get an expansion, which is another representation of x. And this we call lazy. Let me now go to the Luroth series. How do I get these expansions? Actually, what you do is, it looks like the continuous fraction map, or a partition, actually. But I have linear lines. So what you do is, again, my expansion is 0, 1. And I take the partition 1 over n plus 1. Etc. So I take this partition. And on this one here, I I just, on each partition element, I just take complete lines. Of course, now the slopes are not anymore the same, etc. Sorry, I don't like this. You see our lines. The board is not that great. Yeah, anyway, so these are the maps, and I have to look now for the formula because I keep forgetting. Originally, it looks like this. N times n plus 1 x minus n. If you are on 1 over n plus 1, 1 over n, and 0 if x is 0. And here I'm expanding on 0, 1. This is the open at 1. So this is the map. And you can do the same thing exactly. So in here, actually, that corresponds to n is 1. So here the map will be 2x minus, sorry, n is greater or equal to 2. Is it right? Yeah, OK. Yeah. So here the map is, let's see, if n is 1, so you get 2x minus 1. Yeah, OK, that I should have known. And whatever, here is n is 2, so you get 2 times 3, 6x minus 2, etc. So these are the maps. And you can do the same thing to generate the expansion. So you define your digits now to be, I think it should be 2 here, 3 here, 4 here, etc. So you define a1x to be n. If I'm not making a mistake, if you are in 1 over n minus 1, 1 over, no, it should be like this. Or I could, wait, so wait, I want to be 2. So here n is, yeah, 2. Here n greater equal to 2. But it's written weird, so like this, sorry. Yeah. So, yeah. So this is what it is, and 0 if x is 0. So, of course, for 0, it's just 0. I don't have this expansion. OK, and then you can rewrite the map in this way. And if you solve for x, then you get, so this will be a1x, and this will be a1x plus 1. And then if you solve for x and reiterate, you get exactly such expressions. OK, and the continued fraction map, the famous map. This is 5. Of course, it's just tx is 1 over x minus greatest integer 1 over x. And the map looks very similar to this, at least the partition, except that you have hyperbolas like this. Etc. So this is 1 over x minus 1, 1 over x minus 2, 1 over x minus 3. And you can define digits here to be 1, here 2, here 3. And in this case, if you solve for x and do the iteration, then you get the continued fraction map. Then it looks like this, etc. So as you can see, the common denominator between all of them is that there is a map, and if I iterate it, I get expansions. OK, so maybe let's go to maps. So Shigegi gave a little bit, but now let me elaborate more. After I do the ergodicity, but that will be tomorrow, that I will, or I don't know, the Wednesday when I'm talking, then I will go back to this map and show you the dynamical properties. Now I can erase this. So now what I want to do is just some basic concepts in ergodic theory, just really the basis. And then we'll go back to the examples later. Yeah? OK, so maybe here I'll just do basics of ergodic theory. OK, so the idea is we have system evolving in time. And for me, the examples, the evolution is I'm getting the digits one bit at a time. So every time I apply the map, I get another digit. And that's what, for me, evolution is. But basically, you have a set of points. This is a set of states. And you have a transformation that tells you you're thinking of the points in X as moving in time. And this is giving you the evolution. Every time you apply T, you are getting a new state, or the state of your system as it evolves with time. But we want some structure. So depending on what you do. In ergodic theory, we have a measure structure. In topological dynamics, this is a topological space. If you are doing geometry, this is a diffeomorphism, etc., manifolds and diffeomorphisms. And if you're doing symbolic dynamics, this is a set of sequences, etc. But now I want to do a little bit measure theory. So on X, we have a sigma algebra. So these are the events, if you like. We're really doing a little bit probability. And I want to measure things, so that's my probability measure. But in fact, everything I'm going to say is not really important that it's a probability, but what's important is a finite measure. If the measure is sigma finite, then lots of things are not true anymore, and you have to do more things. I mean, there is infinite ergodic theory. There is a whole theory involved in sigma finite measures. But now I want to stick to finite measures or probability measures. And so you have this triple, xf mu, and you have this t. And of course, you want t also to respect the structure, so you assume t is measurable. And this, the quadruple xf mu t, I'm going to call it a dynamical system or a measure preserving system. I didn't do measure preserving yet. Wait. OK, so I have these four things. And I want, skipping a thing, I want the evolution to be stationary. So I want the law that governs the system that doesn't change with time. And that's really the same thing as saying that T is measure preserving. Yeah? So I want T is measure preserving. Which means that the measure of A is the same as measure of T inverse A. So this is the inverse image of A. T need not be invertible. So this is just the inverse image, set of points that get, after application of T, you can land in A. So this is measure preserving. And then the quadruple, if I have such a thing, I call it measure preserving system. OK, Gigi talked about recurrence, but I want to go now to ergodicity, but maybe, yeah. OK, so now I'm going to define what I mean by ergodic. So maybe first, like a picture that people usually use, let me say first what is not ergodic, and then I will make a rigorous definition of ergodic. So not ergodic. So this is my space X. And not ergodic means that I'm able to split my space into two pieces, two disjoint pieces, A and A complement, such that T acts on each piece independently. That is, if I look at points X in A and I look at T of X, then I stay in this region. So T acts on A by just moving around points in A to other points in A. And the same thing for A complement. So this is not ergodic. I want things to move around all over the space. Yeah? So let me write down a rigorous definition, which is really a translation of the negation of this, which says that T is ergodic if whenever T inverse A is A, like in this picture, T inverse A is A, then the measure of A is 0 or 1. Of course, so this means that up to sets of measure 0, the only invariant sets are the trivial ones. Yeah? Okay, but this property of verifying ergodicity, sometimes it's easy to verify something is ergodic using the definition, but sometimes it's not. And there are many equivalent characterizations of ergodicity. So let me list some. So maybe I write it here, tiny theorem or proposition. And this gives you several characterizations, and not all of them, but I'll just list 5, I think. Okay, so let's just say the following are equivalent. Okay, the first one is that T is ergodic in the sense of the definition. And but the definition requires that A to be really invariant. A is equal to T inverse A. And the second characterization is just the same as 1, except you weaken this condition a little bit, because we're doing measure theory, really, and sets of measure 0 don't count. So I can say that I can allow invariance modulo sets of measure 0, which means that if I look at the symmetric difference between A and T inverse A, so these are the points that are in A but not here, or in here but not here. And I look, and suppose this has measure 0. So the set where they differ has measure 0. Then, again, the same conclusion, that measure of A is 0 or 1. And the third one, some kind of I cannot say orbits are dense, but sets of positive measure are dense, in the sense that if the measure of A is positive, then if I move A around via my transformation, and I look at the union, and I look at the measure, then this is equal to 1. So what it's saying is that every point in your space, at some point, it will hit A. Almost surely, with positive measure, probability 1. And the fourth one, which is really reiteration of 3, if everything will enter A eventually, this means iterates of A will intersect any set. So the fourth one says that if the measure of A and the measure of B is positive, so let me just do the product of their measures is positive, so both have positive measure, then there exists an n greater or equal to 1, such that the measure of B intersection T minus n A is positive. So there is an iterate that intersects B. And the fifth one, which is kind of also very convenient, especially if we look at the ergodic theorem, yeah, maybe today, is if you have, see, so far 1, 2, 3, and 4 are characterizations in terms of sets. But you can all do ergodic theory with functions. So anyway, sets are identified with indicator functions. So you can also see sets as functions, if you like. So this says that if f is in L2, or actually just measurable, but sometimes L2 helps because you can sometimes use Fourier analysis to prove ergodicity. So if f is in L2, actually, or measurable, let me just iterate it here. With f, okay, let me write like this. F equals ft, mu almost everywhere. So f is constant on orbits. That's what it's saying. So if I take x, dx, t squared x, etc., and I evaluate f on these points, I get the same answer. So if, mu almost everywhere because you can throw sets of measures 0. So if you have invariant functions, then f is actually a constant almost everywhere. So what it's saying is that if f is constant on every orbit, but a priori on every orbit you might have different constants, it's saying that if you have ergodicity, then you have the same constants on all orbits. Okay, so these are 5 characterizations of ergodicity. I don't know if I want to do a proof or not. You want to see a proof, or they're in the lecture notes? Maybe I'll do one proof. Okay, maybe I'll do just one proof. Let me just do one implies 2. Okay, so let me just do just one of the proofs, and the rest you can read slowly from the lecture notes. So let's just show that if you have ergodicity, that is, if you this property of being really invariant implies measure 0 or 1, implies you have the same conclusion if you have almost invariance. Okay, so I start with let me just pick this in case I forget something. Okay, so suppose I have 1 and I want to prove 2. So let me start with a set A, which is almost invariant. Okay, and I want to show A has measure 0. So the idea is I'm going to now construct a new set, which is really invariant and has the same measure as A. So if the invariant set has measure 0 or 1, the same thing will hold for A. Okay? So I'm going to define, say, B to be the set of points that enter A infinitely often. So I write it like this. M for every intersection, union. So this is the limb soup, actually. So I look at this set. If you read, this is the limb soup, but this says for every m, I have there exists an n bigger than m for which I lie here. So in fact, this is the set of points in your space such that t and x is an A for infinitely many n's. Okay. Maybe if you look at this definition, then it's quite clear that B is invariant. Because T inverse B is the set of points that Tx lies in B. So if Tx lies in B, this satisfies this property, so which means there are infinitely many n's for which Tn of Tx lies in A, but this is a new power, so it's the same thing. So it's really invariant. And by ergodicity, because I'm assuming 1, so I have mu of B is 0 or 1. And now I have to show that B and A have the same measure. And for this, it's enough to show that the measure of the symmetric difference of A and B is 0. Then you get that A has the same measure. And the way you do this is simply write down what B is. Well, the symmetric difference, of course, is A minus B union B minus A, and these are disjoint. So this. And then you plug in what B is. Of course, this is A intersection B complement. And B complement is union intersection. The complement of this, inverse images respect complements. So this is a complement like that. So this is the first one. And the second one is B intersection A complement. So I write B what it is. Okay, let me now think a little bit. So here, what I'm going to do, this is the union. Let's see. So, of course, this intersection is less than the first one. If I just take the first term in this intersection, so this thing here, so the first term is less than or equal to the measure of A intersected with the union of just T minus, I just take the first term, so the mth one. And in the second one, of course, this is the intersection, so it's less than, it's contained in any one of those. So it's contained in particular in the first one. So when I do n is m, so it's the same. So if I take m as 1, so this will be the union here. I should write 1 for m, yeah, that's right. Like this. And of course, you can put the union here. So this is less than or equal. Sorry, I forgot a complement somewhere. Here, yeah. So I put the union here, and it's less than the sum of the measures. And I forgot the complement here as well, no? Yeah, I did. And the same thing here. And I put the sums together, and when I look at these terms, these are really nothing but a symmetric difference. So this is the sum of m is 1 to infinity of mu a symmetric difference T minus m a complement, like this. Yeah, and now I'll leave it a little bit for you. From this condition, you can use induction to show. Let me just write it down because you can see the details also in the note. By induction, just apply induction. And of course, use the fact that you have measure preserving. This also implies that not only is it true for the first power, but it's true for any power. And once you have this, then it follows, because each one have measure 0. So this shows that these two sets, this symmetric difference has measure 0, and this means the measure of A equals measure of B. And since B has measure 0 or 1, the same thing for A. Okay. Okay, so this is 5 characterization of ergodicity, and as I said, there are many, many more. Okay. So now, why is ergodicity important? Why do you want to look at this? Because we have the ergodic theorem and many other things, but one of the crucial things is the ergodic theorem, because it's sort of using the ergodic theorem, you can understand the generic behavior of these expansions. There are any questions? Please let me know. Okay. So before I go to the ergodic theorem, maybe a little motivation, because the ergodic theorem really is a generalization of the strong law of large numbers. So let's go a little bit to probability. Maybe, sure, all of you have seen the strong law of large numbers. But let me just mention it. And just to compare them. Okay, the strong law of large numbers deals with random variables. Usually they write them with x, which now we use them for spaces. But let me use z, maybe. So I have a z1, z2, etc. These are random variables, just our functions on a probability space. So they say random variables, we say measurable functions. It's the same thing. And these are independent, identically distributed. So the probability that zi has a certain value is the same for all i's. Actually, this even a simplified version. Even if you take any n of them, the probability that z1, z100, z200 have a specific value or lie in a certain region is the same for any three combinations, etc. And they are independent, and they should have finite expectation. And expectation, of course, is just integrals. I should do absolute value, but that's okay. Have finite value. And they are all the same because they are identically distributed. And the strong law just says that if you take the average of the z's, and this turns to the expectation of the zi's, and this with probability 1. Okay. But the thing is that this is really restricted. You need independence, and you need identical distribution. Well, this is really crucial. But this you can do without. And this is really what the ergodic theorem is doing. So in ergodic theory, we are interested in orbits. You know what happens to x, dx, d squared x, etc. So now the ergodic theorem maybe before I state it in a rigorous way, let me just write down the analogy first roughly. The z's there is like you start with a function f in L1, because you want the expectation to exist. That's why you do L1. And the sequence you get by looking at f at orbit. So the corresponding sequence will be f composed with t, f composed with t squared, etc. So this is z1, z2, z3, etc. And the ergodic theorem, actually, essentially, you only need measure preserving. So you have t measure preserving. This is essential to get a convergence of the averages. But if you want them to go to one answer, then you need ergodicity. So the ergodicity is replacing independence. Because actually, ergodicity, you will see it as a corollary of the ergodic theorem. It's some kind of a weak independence. Yeah? So f composed with t, so this is your sequence. Measure preserving is exactly identical distribution. It's really the same translation, the same property, except this is probability language, and measure preserving is ergodic theory language. And independence is replaced by ergodicity, although now maybe not apparent, but as a corollary, you will see that it is really some kind of independence. So if you have these two properties, then 1 over n sum f ti x, ti, I from 1 to n. Let me evaluate at x, because then I say mu almost everywhere, that this converges to the integral of f, mu almost everywhere. So on a set of on a set of probability 1, of measure 1, you have such a convergence. So there are bad points where this doesn't work, but this has measure 0. So this is really the strong law of large numbers, except written in an ergodic theory language, and independence is weakened to ergodicity. So it's the strongest you can get. You cannot weaken this anymore. So if you want to generalize the strong law of large numbers, this is the most you can get. I need some water. Okay. Now, there are also many versions of the ergodic theorem. This is what people call pointwise ergodic theorem. It was proved by Berkhoff. And simultaneously, actually, there is, von Neumann gave an L2 version, that is convergence in L2. And there was a competition who did first, and actually they appeared in the same journal. One L2 convergence, and the other one is pointwise convergence. Usually pointwise convergence is harder to prove than L2 convergence. But after, and there are several proofs. There is I like a modern proof, which is proven by Keen and who? Kamai. Yeah. I like this proof very much, actually. It's very elementary. It's just breaking your orbit in a clever way. I have the tendency of giving the proof. I don't know if anybody saw this proof before. Maybe that's what I will. Okay, maybe I will do half of it today. I will prove only one part. I will at least give you indication of the proof of the steps. Okay, and the proof relies on an almost trivial lemma. So before I write down the proof, let me just write a lemma. And it's a lemma on sequences of real numbers. And it's really an obvious lemma in a sense. So let me just write it down. So you have I pick an integer m, but now it's not apparent why, but it will come down in the statements. And suppose I have two sequences of real numbers. Non-negative, I think. Yeah. Okay, now M will come into play such that for each n bigger or equal to 1, the small n is the starting point. So let me just write down a sequence. So here's, I think they start in 0, but it really doesn't matter. Let me start it with 0, that the sequences start, n is 0. So here's my A0, A1, A2, etc. And here's my B's. And now what I want to say is that if I pick any position whatsoever, that's the n, if I take any position whatsoever, and for each n, there exists an m between 1 and big M. So if I start in any position and I take a block of length small m, which is at most capital M, and I compare these two parts of the sequences from position n to position n plus m, and if at every such comparison I get the A sequence bigger than the B sequence, wait a minute, let me see, such that for each n exists with A n plus blah blah blah, A n plus m, minus 1, because I'm thinking of 0 beginning in 0, bigger than the corresponding b's. So every chunk of length at most big M, and how big it depends on the position. If the A's are bigger than the B's, then in fact the whole A sequence is bigger than the B sequence. Then for all n big enough, then for each n bigger than m, if I look at the sum of the A sequence up to n, minus 1, I suppose, if I want to be very correct, because then I'm taking n terms, is bigger than the corresponding B, but I have to remove the last m bits because I don't have space to compare, like this. So I'm just removing a bounded amount of the B's. N plus m, say it again?
You are removing something from B, but you are adding something in the index.
Minus, that's exactly. Thank you. That's kind of obvious, right? If you per block you have such a thing, then if you take the whole thing, it's bigger. But the only thing is at the end, I might not have enough space to compare the last block. That's why I stop here. Okay. So, okay, so let me do just one part of the proof, actually. So proof of ergodic theorem. Okay, so first of all, remember these sequences have this property non-negative, and f can be, it's any integrable function, but of course we can write f as f plus minus f minus. So I'm going to assume with no loss of generality that f is positive, otherwise I do the positive part alone, the negative part alone, etc. So assume f is positive. And the first thing I'm going to do is I'm going to look at the lim sup and lim inf. And also to, because I'm always going to look at summation, so I'm going to do some shorthand. So I'm going to let fn to be the sum of the first fx plus ftx, etc., up to n minus 1. Okay, just shorthand, so I don't have to write this whole sum. Okay, and now I'm going to look at, I'm interested in this. So in my notation, this is 1 over n fn now. And I want to show 1 over n fn converges. So I look at lim sup and lim inf. So I'm going to call f upper bar the lim sup of fn over n, and the lower bar the lim inf. Okay, and now before I do anything, let me just show that these two are invariant functions. In fact, every time you do such a thing, you take limit or lim sup or lim inf, you get something invariant. So let me just show f upper bar is invariant, because the same proof for f lower bar. So f upper bar is t invariant. That's the claim, which means what I'm saying is f bar equals f upper bar equals f upper bar composed with t. And this is actually kind of simple. So if you look at f upper bar of tx, so this will be lim sup of fn tx over n. But fn is the sum of the first n minus 1 terms. But here I'm starting with tx. So in fact, fn of tx is like doing ftx up to fnx. So in fact, this is lim sup fn plus 1 of x minus fx, and I divide by n here and here. Yeah, if you want to be very exact, I divide by n, but I want n plus 1, so let me do just something stupid like this. Okay, and I'm done because this limit exists, so this goes to 1, this goes to f upper bar of x, and this goes to 0. So this is really f upper bar of x again. Okay, so these functions f upper bar and f lower bar are t invariant. Okay, and now to finish the proof, to prove the theorem, what you need to do is the following. So to prove the ergodic theorem, we show the following. That the integral of f upper bar is less than or equal to the integral of f. And remember, f upper bar is this, and this is less than or equal to the integral of f lower bar. If I do this, I'm done. Why? Because, of course, f upper bar is greater or equal to f lower bar, so this is really saying that this will imply that f upper bar, minus f lower bar d mu has measure 0, is less than or equal to 0, but it cannot be because this is positive. So you get that this will really come down to show, this will imply that this is 0. And this is a non-negative function. And if the integral of a non-negative function is 0, that means that the function itself is 0 almost everywhere. And once you get equality, then the limit exists, an equal lim sup or lim inf. So it boils down to showing this inequality. Yeah? So I will just do this because the proof of the other one is very similar. Or maybe steps of it, because I don't know, I have to stop at 1:45, right? Yeah. Okay, so just steps. Okay, so what we're going to do is, we're going to have some epsilons and some, because I don't know if the lim sup is infinity, so we have to truncate things. So I'm going to also have an integer or a real number L. So I pick an epsilon, and I think between 0 and 1. Let me see. Yeah. So I pick an epsilon between 0 and 1. And I pick a real number or an integer, whatever, greater than 0. This I will send to infinity in a second. Okay. So these are given and fixed. And by definition of the lim sup, so if I, so let's just here, by definition of lim sup, I know that for every x, I can find an m such that f m x over m is greater or equal to, if I, and here I'm going to shrink the lim sup. So if you shrink your lim sup, you're going to be above it. Okay, and this I can do for every x. So this means that given this epsilon, I can find a delta such that, now for any delta, I can find a big M such that the measure of the set, such that the set, let me call it y, of all points for which I can find a small m between 1 and big M, such with Fm greater than this shrinking that I made, that this has measure bigger than 1 minus delta. And this is simply because this is satisfied for every x, I can find an m. So if you want, I can make, for every m, I can make the set of points for which this is satisfied, and these increase to, then for every m, I look at such sets, and these cover the whole space. So if I make m large enough, I can cover 1 minus delta of my space. Okay, and now what I'm going to do, we're going to change small f a little bit so that things work well. So I'm now going to define big F as a small f if I am in this good set, and if I'm not in this good set, if I'm in the bad set, then I'm just going to make capital FL. So I'm actually truncating f outside y. Okay, then, and this I'll leave it for you, then this big F dominates small f. The small f is less or equal to big F. You can just look at the definition, then you can see that. Okay, and now comes the lemma, which I unfortunately erased. So now I'm going to define AN and BN sequences related to these things. So I'm going to define AN for each x. I'm going to define a sequence. So I pick an x and I define a sequence AN corresponding to it and a sequence BN. And the AN is simply the f composed at t and x. And the Bn, in this case, is a constant sequence. It's a bit stupid, but the whole thing is that their proof actually was not only for the ergodic theorem, which was for the ratio ergodic theorem, and then the Bn was not constant, but then the proof works also for this case, and then the Bn becomes constant. So this is just what I have here, minimum. So it doesn't depend on n, and that's because f upper bar is t invariant. So in essence, it should be minimum f upper bar of t and x L times 1 minus epsilon. But because f upper bar is t invariant, then I don't need this. So the Bn sequence is constant, and the An sequence depends on n. Okay, and then also I will leave it for you. Now we can verify that the sequence AN, that for each x, the sequence that we construct, so now I can put x, and Bnx satisfy the lemma with m. In the lemma there was an m, how big the blocks will be, and the m is exactly this m that we found here, for which this set has measure 1 minus delta, at least 1 minus delta. So the AN and the BN sequence satisfy the lemma with this M. And once we have this, it's just, it's almost done now. Okay, so now what we do is we apply the lemma. For any n bigger than this m, so for n sufficiently large, the AN sequence is bigger than the corresponding B sequence, but the A sequence is made from the F's, so you get Fx plus Ftx plus blah 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 Ft, what was it, n minus 1x. This is the AN sequence, is bigger than the corresponding B sequence up to the last m blocks, and the B sequence was this, and it's a constant. And I'm going to stop at n minus m minus 1 or something like this, so I will get n minus m because I'm starting with 0. So I get n minus m terms that are identical, and each is equal to minimum f upper bar x L times 1 minus epsilon. Yeah, this is simply the lemma. Okay, so now I divide by, I now integrate both sides. I integrate both sides. Okay, and one thing I didn't mention, but measure preserving, we said like MA equals, mu A equals mu T inverse A. That's in terms of sets. And if you write this, so this is like integral of indicator functions. And if you look at integrable functions, then this is also equivalent. So measure preserving is also equivalent to saying that integral of any f, any L1 function, is equal to the integral of f with t or f with any iterate. So that's exactly the same. So when I integrate, I get the integral of this plus this plus this, but they are all the same because I have the t's in there, and I have n of them. So you get n times the integral of capital F is bigger or equal than n minus 1, n minus m. I can put 1 minus epsilon out, and I get the integral of minimum f upper bar L d mu, like this. And then let's divide by n minus, by n, sorry, because I'm interested in this. So I divide by n. Okay, I'm going to erase. Like this. So, okay, and now I'm going to send things to infinity. So now I send n to infinity. So first I do n going to infinity. This becomes 1. So this goes away. I send epsilon to 0. This goes away. I send L to infinity. And of course, this converges to f upper bar. And then you will, this will go to integral of f upper bar d mu. So far what I have is, was I too fast? I was a bit too fast, because this is for f, capital F. I want to go to small f. Okay, I was too fast. But okay, let me just fix it up by just telling you. Of course, I can go from capital F to small f in an easy way, because they are equal to each other on y, and they differ on the complement, and the complement has measure 1 minus delta, and then I send the delta to 0 as well, and then I get that the integral of capital F will be replaced by integral of small f. Yeah? So this gives you one side, and then the other side is really very similar to this one. So I think I'm done. It's very tiring after an hour and a half.